Hello, welcome to the Machine Learning at Home. Today I will speak about some unusual measure of the distance. This is called normalized compression distance. I think you dealt with zip archives, so there are many ways to compress computer information in some file of the smaller size. But what is interesting, many ways of compression depend on amount of information within the object. For example, if the text consists simply of one letter A, that will be compressed much better than like a Shakespeare piece. So this is interesting, and that might be used for interesting reason, to measure similarity between two objects. If we make one object out of two, compress it and measure how well it is compressed, and then compress each of object separately, we will find out how close are they to each other. So if they kind of similar, if there are two documents, one of letter A and one of letter B, they will be compressed in a similar way, like a Shakespeare piece will be compressed in a similar way if we take two different Shakespeare things. So this is what I mean by normalized compression distance. A very interesting, unusual distance, and what is very good about it, it is absolutely universal. It may be applicable to almost anything. Let me show how it works. So first of all, you will need my package, library Shipunov. And please be sure that you have a latest version 1.16 or later, because this function was only recently introduced in the package. If you do not have a latest version, please update it and then use this version, which is 1.16 or later. Okay, and if you have version 1.16, you will have this function. Let me show it on an iris example as usual. So iris example is not very good working for that reason, because if you remember, there are only 4 characters. So we'll use only vectors of 4 elements for compression, very short ones. They should be much longer vectors, well, to make this function work properly. But it is a good demonstration anyway. So first of all, we use nc.dist. This is a normalized compression distance. And then we'll apply it to the iris object, as usual, without character number 5. Actually, we can leave it here because distance is universal. Why I take it out? Because it's kind of cheating. This number 5 contains the name of species. If we leave it in a data, then the answer will be provided in a task, and this is not very good. So we'll remove it, not for formal reasons, but for kind of sensible reasons. And then we'll write the result into some object. It will take time, and we have now result. So it works a bit slower than typical distance function, most of all because this is not very much optimized. It uses only R routines, not like a C code or anything else. Anyway, it works fast enough for this data, will work much slower for the bigger data, and they will need to somehow understand what we have. So we have a distance matrix. How to show the distance matrix to see how it works? Well, one of ways is clusterization. So we'll use some clusterization, for example, function hclust. hclust, and we'll take this iris and see the distance matrix and use some very sharp methods of clusterization. For example, word z2 is one of 2 methods embedded in R. And of course, we'll write result in some new object. So iris and C, for example, example, H and C. Okay, H and C will be the better name, I think. Okay, and then we need to show it. So we need to make a plot. So a plot probably will be principal component, well, projection, and will colorize clusters with some color. So let us produce this colorization rule, and I will simply, well, extract 3 classes, simply because we know there are 3 iris pieces. So I will call this 3 classes object iris pred, like a predicted classes, and we'll take it from a hierarchical clustering with a function cu3. And I will need to take an object H and C, and I will provide number of clusters, 3 in that case. Okay, so this cu3 function will simply find a place where we see 3 clusters and will number each of them. And finally we need a plot. So we'll need a plot, for example, results of the principal component analysis, which is simply projection of our data to the 2-dimensional plane. So we'll take our data again, iris without character number 5, and from that PRComp result we need to extract part of object which has name x, and then we will and we'll need to colorize with our iris.pred. Okay, sounds like I did it. Yep. So as you see, it is not perfect, but good enough. So for example, this cluster is almost all black. There are 3 red dots, so this is some blurring of classification. Some black dots appear on the right side as well, but only few. And 2 other closer pieces of iris are separated more or less well. We can even try to measure it as in some kind of percents with my function misclass. So misclass from iris predicted classes, and now we have a initial classes. This is character number 5, which we took out all the time. Iris $species. I call it by name. Oh, and I forgot, of course, most important part, best equal to true. So this is one of wonderful features of misclass function. It will, well, compare classification even in case when classes do not have names, like in our iris pred object. So we need to try seed. Okay, so misclassification, the lowest misclassification error is 24%. It's quite high. Yes, I understand it quite well. But please remember, we only deal with vectors of 4 members each, and kind of compression functions will need much longer vectors. So maybe with hundreds and hundreds of characters, situation will be much better. But what is most important, this might be worked with anything. So it might be any character, numbers, some phrases, whatever. You can use language objects, you can use DNA sequences, whatever you like. This is most important thing about this compression, normalized compression distance. So normalized compression distance is not very precise, but this is compensated by absolutely agnostic nature of this distance. So very agnostic, which is very good for some statistical applications. And of course, everything should be paid for. This is less precise than other distances. So this is a normalized compression distance, which is used compression, zipping of object to understand how similar are they to each other. Thank you very much. This is it.